Hello. I want to use this video to look at a couple of practice problems. We'll call this set 1, and the main type of problems we're going to be looking at are elimination problems that we have to predict the product, we have to show the mechanism, either E1 or E2. We should be able to predict whether the major product is the Zaitsev or Hoffman alkene, and a new type of problem in which we're given the final product and we have to propose a starting material, alkyl halide. Now, there's a couple of topics that some of you may be familiar with that we will not cover on this problem set, and that is this idea of anticoplanar conformations in E2. If that doesn't ring a bell, or if you're not familiar with that, don't worry about it. And also, we're now going to go over a decision tree to decide whether a reaction undergoes substitution, elimination, or possibly both. That is reserved for a more upper level topic. So overall, these practice problems are going to be based on two early videos, 08B20 and 08E20. The first problem, and we'll just number this sequentially. Number 1, draw the elimination. So I have S in parentheses, so it could be one product or it could be many products. I typically want all the alkenes that are possible, and draw the mechanism. For problem number 1, we're going to look at one reaction, and it's going to be this alkyl halide, alkyl chloride specifically, and a very popular strong base, NaOET. Okay. If you're copying these problems, go ahead and pause the video. That's the problem right there, all in black. My notes will be in green. My final answer will be in blue. We want to draw the elimination products, and well, my notes are going to be in green and pink. So this is the alpha carbon. We have a beta to the left, a beta to the right. So if we use the beta on the left, remember this is called beta hydrogen elimination, we are going to make the double bond to the left. And what do you eliminate? You eliminate obviously the leaving group, but also what's called the beta hydrogen. This is a strong base, and whenever you see an alkyl halide plus a strong base, you're going to think elimination. And the problem actually tells you elimination. Okay. There's some instances when the strong base can act like a nucleophile and that you'll get substitution, but again, at least for some people, we don't need to know how to decide whether it's substitution or elimination. I'm telling you that it is elimination that I'm interested in here. When you draw your first alkene, you want to ask yourself, is there a possible cis-trans isomerism? But because this carbon here has two of the same groups, two methyl groups, this cannot be cis or trans, and you would not make isomers when you make the double bond to the left. You can also make the double bond to the right, because there's a beta carbon to the right, and you have this. Again, there's no cis and trans for this alkene, so you don't have to draw its stereoisomer. These are the two products. It says draw the mechanism. I would not ask students on an exam to draw the mechanism for multiple products of the same reaction. So I would say here, draw the mechanism for the major product. Okay, do you see that? Draw the mechanism for the major product. Well, that means that we have to decide what the major product is. put your dots on the double bond carbons and ask yourself, how many substituents does it have? This carbon has 1, 2, 3 substituents. This double bond has just 1, okay, and the other 3 are hydrogens. So here this molecule has 1 hydrogen off of the double bond. This molecule has 3. This is more substituted. This is the major. And this is also the Zaitsev product. I think we have an example later where we're going to draw the Hoffman product, the less stable, as the major product. Okay. They want us to draw the mechanism. You want to draw the starter material first, the main starter material, and then you got to realize that this NaOET is actually what? It's actually epoxide. The sodium dissociates off, leaving behind an O-. The major product was using the beta carbon on the left, and I'm going to cheat a little bit. I'm going to make this the hydrogen. So that carbon still has a methyl group, 2 methyl groups. And here's our beta, and here's our alpha. This is this is an E2 mechanism because we have a strong base. So when you have a strong base, also realize that it's going to be E2. Okay. I said my answer will be in blue, but to make my mechanism arrows pop out a little bit better, I'm going to draw my mechanism arrows in green. Okay. So that arrow should technically be pointing directly at the chlorine, but this is the leaving group. I think this is good enough. What I'm saying actually is putting 2 electrons as a lone pair on chlorine. There are 3 mechanism arrows for an E2 mechanism, and we are done. That's your product. If you want to draw out all the products of a step, then you also produce this ethanol, and you also kicked out a chloride. You don't have to draw the lone pairs if you're not using them with a mechanism arrow. So you notice that I didn't draw the lone pairs on chlorine, but I definitely drew the lone pairs for oxygen. Okay, so that's number 1. Predict the products, plural. Select the major, draw the mechanism. Number 2. Let me show you a reaction where we get what's called the Hoffman product. I'm just looking. Okay, this one right here. Do I have to? Okay. Draw the, and I'm just going to abbreviate elimination with E. Products. And instead of drawing the mechanism, I just want us to state if it's E1 or E2. Okay? And we'll learn shortcuts so you don't have to literally draw the mechanism to figure out if it's E1 or E2. We should be able to, actually we should be able to decide that even before drawing a mechanism. Okay. The reaction here is going to be this one. This one's interesting. The way that I'm seeing it on the set of problems is this reagent. I am giving you the clue that we want to do elimination. In terms of my analysis, this alkyl halide is tertiary. So it can make a pretty stable carbocation. So that maybe points us to E1. But if you look at this molecule here, what is this? And the way they drew it, there's a hyphen there. I actually think of this as KO-T-butyl. Because why do I like looking at it like this? Because I see the metal, and I know that it dissociates off of the oxide. See, the K is next to the O, and the T-butyl, superscript T, tert-butyl, the crow's foot, and I have this. This is a strong base. And on the video, regardless of whether the alkyl halide is primary, secondary, or tertiary, if you have a strong base, you are going to definitely do E2. So in a box, I'm going to write the mechanism is following E2 pathway. I haven't drawn the products yet. Okay. I have to draw elimination products. You have an alpha, you have beta, beta, beta. Okay. Now, hopefully at this point you have enough experience to understand that if I make the double bond between this alpha and the beta on the top, well, let me draw it, and I think you'll see that we're going to have some redundancy. Let's take the beta carbon on the left first, though. Okay, that takes care of the beta carbon on the left. My question to you is there any E and Z isomerism here? No. Actually, both carbons have two groups that are the same. Like this carbon on the left has a ring, and the ring is symmetrical, and this carbon on the right has two methyl groups. There's no such thing as E and Z for this case. But let's draw the double bond for this using this beta carbon. We have that. And beta alpha. So my contention is that even though we see 3 beta carbons, we actually only have 2 products, because if I made the double bond here to the right, hopefully you could tell that it's identical to this by just rotating this bond right here, the one that I'm pointing to. Does it say which one's the major? Let me add that so the question is exactly correct. Circle the major. Awesome. Tetra substituted. There are no hydrogens on the double bond carbons. What is this? This is di substituted. You have 2 hydrogens, you have 2 groups, 2 and 2. This is 4 groups, 0 hydrogens. The major product. Oh. Oh no. I could hear people screaming at me through the video. That's not the major. Man. How come that's not the major? Those of you who watched those first 2 videos for Unit 8, what kind of base is this? This is an bulky, crowded. Okay. Good thing I didn't turn in my exam yet, because I caught my mistake. And I realized when you have this crow's foot, this tert butoxide, okay, it's a strong base and you're still doing E2, but it's so crowded here, the probability of this oxygen reaching into this crowded spot to grab the hydrogen is less likely than grabbing it off the end of the molecule. So we're now using crowdedness because this is too bulky to remove the beta hydrogen on the left. If that's true, then you'll remove the hydrogen on the less substituted, less crowded beta carbons, and it doesn't matter which one because, like I said, you'll get the same product whether you remove the hydrogen up here or down here. Yikes. So this is now the major product. But you notice that it's not the most substituted alkene because we can't. It's too crowded to make the double bond on the left. Maybe it can, but it'll be at low percentages, maybe 5%, 95%. Okay, that's how sensitive this is to the size. You know, in our first example, our base is pretty tiny, so we can sneak into the more crowded carbon and take this hydrogen to give us, the more substituted, more stable alkene. Okay. This alkene, when your major product is the less stable alkene, that's called the Hoffman product, or the Hoffman alkene. Ooh, yikes. Alright, so while I'm studying for the exam, I gotta be careful of this, and I'm gonna use these as my study notes, and I'm gonna put yikes. Okay, and that will help me, hopefully. I see this X right here. Hopefully I know that this check mark is the major product. For most students, there's only one example of a bulky crowded base, and it's this potassium tert butoxide, or simply tert butoxide. Okay. For other students, or if you read the textbook, there are a couple more, but this is the main one. Okay. Yeah, pretty happy that I caught that. Shall we take a look at... Yeah, let's take a look at... for us, this is number 3. And it's saying draw... This is a structural formula. I don't know why. I'm taking this off the textbook. When I say structural formula, it's just the molecule, and I think of this as the line angle structure, or line angle drawing. We're dealing with alkenes, so most likely there's not going to be any chiral carbons or any imported chiral carbons, so I should not be seeing any wedges and dashes for any of these problems. It says draw the structural formula when the following is, we could say treated with, and they spelled it out. They're not giving us the formula. Sodium ethoxide in ethanol. Don't let extra molecules in your reaction distract you. You know that we're going to have an alkyl halide. You know we're going to have this is a base, sodium ethoxide, NaOET. This is just a solvent. Don't let it bother you. Okay? You still understand that we're going to do an elimination. And I'll write that actually here. Assume. The problem actually says assume E2 happens. Okay. Not only do we know it's elimination, they're telling us that's the E2. Which one do I want to use? As long as I'm talking about don't let things that aren't that important distract you, let's have that alkyl halide. And see, the problem says this is a problem in black, okay? And they expect you to draw the product, okay? But when you're practicing, I would draw out the whole reaction. Get practice. Draw what sodium ethoxide looks like. So I'll do this in blue because technically this was not provided. The formula wasn't provided. And ethanol, that's this. You could abbreviate it ethyl alcohol, or CH3 CH2OH, right? Or something like that. Okay. But that's my reaction. This is just a solvent. For eliminations, it doesn't play that big of an effect in terms of deciding what happens. Okay, it's not like substitution where you have protic aprotic versus protic polar. What did I say? It's not like substitution where you have polar aprotic versus polar protic to help decide SN1 or SN2. This one, it doesn't really matter. What matters is that you have this NaOET. It separates, and you have here a strong base. They didn't have to tell us that it's E2. The fact that it's an alkyl halide with a strong base, that tells me that it's E2. Alpha, beta, beta, beta. Did they say major product? They actually put a plural here, structure formulas, because I have multiple beta carbons. I think that I might have multiple products, and here's one of them. Okay, I like trying to draw the molecule with the correct bond angles, right? So we do have 120 because that carbon is trigonal planar. So it's the double bond between this alpha and beta, plus. Okay, again, trigonal planar, and I'm using this beta up here. If I use the beta over here, it's going to give me the same product. And the major product now, this is not a bulky base, so we're following Zaitsev's rule. Major. And in this case, the major product is the Zaitsev product. This is called tri-substituted. This is called di-substituted. I know I'm running through this a little bit fast. I'm showing you in real time how I would do this on an exam, but of course you could rewind the video and put all the notes also, because I said this was tri-substituted. This is di-substituted. I want to let me do 4, and then I might come back to one of these to discuss cis and trans isomerism. If I don't, then I'll probably do that on problem set 2. But I wanted to get to problem 4 because this one's interesting. It says draw the starting we're going backwards here. They give us the product, we give them the starting material, the alkyl halide. Draw the starting material, alkyl halide, that if treated with potassium hydroxide, so you gotta visualize that this becomes OH minus, that's a strong base. We're doing the E2. So draw the starting material alkyl halide that if treated with KOH gives the following alkene. I'm rushing a little bit, as a major product. And this is what I see. Okay, so that's one example. A. Oh my goodness. So what are they asking? What they're really asking for is, if I treat something with KOH, what is that alkyl halide originally looking like? Question mark. Okay. Now, did you realize that every time we made a double bond, that double bond was made between the alpha and the beta? So one of these carbons has to be the alpha. Alpha beta, and in this case alpha beta. So that means that the halide has to be on one of the double bond carbons. I like to use trial and error. So I'm going to draw the carbon skeleton, and I'm going to guess. Okay, I'm going to guess that, well, let me put the chlorine on this bottom carbon. Okay, so it doesn't matter which halide. I'll use chlorine since I started with chlorine. And I'd say classmate. It says correct. So I asked my classmate, what would you draw if I gave you this alkyl halide with KOH? Because I put the halide on one of the double bond carbons. Well, your classmate will draw this. Hopefully. I can make the double bond here. Okay, because that's a beta carbon. And I can make the double bond down here because that's a beta carbon too. And hopefully your classmate will also say that this is a major. I think we've satisfied the requirements. So forget about the alkene that they want us to make. My proposed alkyl halide is this, and I give it to a classmate and I say, can you double check what kind of alkenes I make when I have these two react with each other? Well, they're going to say, well, this is a beta and this is a beta. We'll get two products, and the major one is the one that's tri-substituted. And is that true? I want a starting material that will give me this as the major product. Check. So this is good. This is an answer. Answer. Check. But there's also another answer, I think. What if I have this? What if another classmate put the chlorine on this top carbon? Would they be correct also, or would they be incorrect? Okay. So again, this is proposed. You have to be comfortable using trial and error. I think that's a lot faster than trying to do this on scratch paper or in your head. Just propose a reasonable structure and ask a classmate, alright, classmate, what do I get if I give you this alkyl halide? So there are actually 3 beta carbons, but 2 of them are identical. Okay, so I can have that plus, I get a different alkene if I use the beta carbon on the right, and I get this. I will circle the major product, and then I will ask, is that what I wanted? This is another answer. Oops, not this one. This is another answer. Check. Ultimately, what do we know? There are 2 alkyl halides that when you treat it with KOH will give you this product. So there are 2 answers. That's the game you want to play when you have to go backwards and figure out the alkyl halide. Because I won't have time to do it here, but what about part B? Okay, what if they gave you, interesting, maybe we'll start with this one on the next problem set. That. Okay, are we going to get 2 answers like for part A, or are we only get 1 answer? Or maybe even get no answers. Maybe it's impossible to have an alkyl halide that will give this as the major product. Okay, and actually this one's actually easier. Let me give you a harder one. If you want to be challenged, how about this one? So these 2 do at home, or we're going to see maybe the next video, problem set 2 for these 2. Okay. All right. Go over these problems. You totally have the opportunity to recopy the problem without the answer. Okay. Or you could pause the video. You could rewatch this video again and pause it before I start drawing the answer.